Srivastava sir, all yours. Srivastava sir, we have started.
A very good afternoon and a hearty welcome, Dr. Seema Vinayak and Dr. Madhusudan Reddy. We just had a very interesting session on materials for aerospace. Though we are running a little behind schedule, but that should not constrain us from debating during this very, very important session on materials for missiles, guns, as well as warships. We have a a host of very, very distinguished domain experts here with us, and Dr. Madhusudan Reddy, in fact, on a very short notice. So, despite he was not keeping very well, on a request, he agreed to join us to give a special talk before the session per se commences as with Dr. Seema Vinayak as chair. So, a very short introduction for Dr. Reddy. Outstanding scientist and director DMRL is in order. He is an accomplished scientist, very well known, of great repute. He has made significant R&D contributions in the field of materials, especially in joining and surfaces, which have a direct application in defense and aerospace technologies. He's also developed a technology for welding of low alloy steel shafts for aerospace programs. And he has a string of achievements to his credit, having been at the spearhead of path-breaking achievements of the DRDO for long years. So, thank you so much, Dr. Reddy, for joining us. It's over to you.
Thank you very much for the introduction, and I'm very thankful to Sunil Srivastava and Major General Ravi Arora for giving an opportunity to share some of my thoughts on this particular activities. Are you able to see my screen?
Yes, sir. Yes, sir.
We can see your screen.
Second slide also, you're able to see that?
Yes.
Okay. So I'll be talking on materials for defense application. Okay, I'll be more of emphasizing on missiles and other programs. And we at DMR in the area of working in the area of metal sciences, solidification technologies and forming technologies, and powder processing and extractive technologies for various products related to aero, naval, and armor applications. As you know well, okay, our core competence is right from basic understanding of material behavior, design, and development of new alloys, new processes for production of metallic alloys, ceramics, and composites. In fact, DMR has largely been excellent in the laboratory, and our future activities in the area of accelerated material development using integrated computation methods, engineering, AI, and MI. DMR being a materials lab has project activities almost with all the clusters of DRDO. And these are the cluster-wise thrust areas, which is, I'll be giving only one or two examples of this cluster, what we are working because of limited time. And when it comes to the protection of armor technologies, in fact, armor protection is one of the most secretive technologies, generally not revealed by any country for its fighting platforms. Over the years, in fact, DMR has successfully developed, provided various armor solutions for different applications, such as Arjun MBT, Abai, Lancer, and Mi-17 helicopter, body armor, armor for bus, and wheel armor platforms. In fact, we have developed many materials, and we have a good collaboration with various academic institutions and our sister laboratories and international collaborations. And in the coming years, okay, because we are going to work on mainly on blast mitigating armor technologies for mine protection vehicles, as well as we are working on light armor against Canad 5 and 6. And also we are going to work on human survivability technology against blast. These are the main activities. When it comes to penetrators, okay, in fact, we developed the kinetic energy penetrator and productionized it, HEPP have. As a protection capability of tank armor has enhanced over a period of time, there has been a demand for heavy alloy ammunition with higher depth of penetration. So what we are going to do in this coming years is this is the slide shows the past development as well as future horizon extending up to 2035 with respect to kinetic energy penetrator. And we are going to work on development of high depth of penetration by alloy chemistry modification, refinement in thermomechanical processing, and establishment of process structure and property correlations for getting high depth of penetration. When it comes to missile and strategic systems, okay, maritime steel is used extensively both for space as well as our missile programs, mainly for the motor disc applications. And why this is so important? Because it's a low carbon, and we are able to get unique combination of strength, excellent fracture toughness, and good weldability. We can able to machine to the nearest dimensions, and there's no dimension change for the subsequent processing or subsequent treatments. And we are able to get the strength by simply aging treatment by getting fine intermetallics. The problem is here, okay, whenever you are trying to weld it, there is a segregation of moly and titanium during welding, because this causes local enrichment. This causes local enrichment at the interfaces, and subsequent aging treatment, we are getting riveted austenite. That is basically a subphase. During pressure testing, okay, during actual loading, this is getting yielded, and we're getting a lot of voids. All voids are getting connected. Most of the casings are during proof itself as failing. Okay, to overcome that one, okay, why can't you have lower moly and titanium in the welding pillar? Okay, and if you reduce the lower end moly and titanium, and there is reduction in strength, so that can be compensated by adding aluminum to cobalt. But even though problem persists, and we're able to minimize the formation of riveted austenite, but we can able to control the elemental segregation by changing the process. For example, if you go for laser, you go for pulse laser, there is no segregation of moly and titanium because of the fast cooling rates. Even if you're using TIG welding process, after welding is over, you have to homogenize it, then go for aging, and that is very difficult in actual applications because most of the things involve components. So we cannot use this kind of a treatment. So how to enhance the fracture toughness? Okay, so the best thing is, why can't you look for a process in which there's no melting at all? And these are, I'm showing, these are some of the solid state welding process, and there are several challenges in the welding of using this process for welding maritime steels. I'm showing an example of friction stud welding. It is a non-fission process, and there are several challenges because when you're trying to weld it, you need a tool. The tool should have good mechanical properties, high temperature strength, good wear resistance, and manufacturabilities. And we consider these are the tool materials, tungsten-based or abrasive materials. And during welding, because the operating temperature is quite high, and there are quite stresses on the tool. So we have developed a lot of materials, and we have studied a lot of activities by using tungsten-based alloys. Tungsten lanthanum-based alloy, we can able to weld maritime steels, even for thickness up to 15 to 20 mm thick, it's possible to weld. And in the process, we are able to get no melting involved in that, and we are able to get good fracture toughness. And this technology is already proven, we are going to implement in actual applications. And we have established a wide range of the process parameters, how to weld this kind of a material by using this process. And we are also working a lot on development of high temperature materials for hypersonic vehicles. And in fact, we have just concluded one project. We gained a lot of expertise in production of carbon fibers and carbide for the airframe and wing leading edges and cap, and so on. And we also developed the nylon-based alloys for the scramjet combustion chamber applications, and we established the necessary coatings, and also we established thermal protection systems to cut down the temperature from 950 to up to 50 or so. And in the process, we developed a lot of facilities to evaluate these materials under hypersonic conditions, and we could able to establish the facilities and the materials at laboratory scale. And in the coming years, okay, in the very near future, okay, we are going to work on the issues related to manufacturing and fabrication to realize the components. And right now we are in phase 2 program, and we got a project very recently, and we're trying to scale up the materials, and we're able to make the components and also related quality excellence issues. Then we are going to enter into phase 3. We are looking for the materials for reusable vehicles and so on. DMRL is having a lot of expertise in using powders to produce components of dual property, superalloy blanks, and we're also using this slipping technology to heal the defects for various aeronautical applications. And because since we are having a metallic powders, we are having a lot of expertise, then we ventured into another activities. Can we be able to make with ceramic powders to produce a radome, okay? Presently, they're producing radome with silica using the slip casting route. The yield is quite low, and radome is the most important part of a missile, which protects the navigation system of a missile from adverse environment without affecting the electromagnetic performance of the antenna. In fact, we have used the whole isostatic pressing technique, and we have developed the technology and understood the powder, the size distribution, and so on, and we could able to make the radomes for our Astra and QSM, and in fact, we transfer the technology to the various industries. And today we are working on a separate project. Can we able to enhance the flexural strength of this particular material for high-speed missiles? And we are working silicon nitride as well as the modified future silicon and so on. As you know well, until recently, a majority of the raw aluminum alloy products required for the both armor as well as aerospace applications were being imported, resulting in issues of quality, time, and cost overruns. Having decades of in-house research, design, and development of experience, close interaction with users and inspection agencies, in fact, we could able to produce variety of aluminum alloys and desired semi-product form, that is extrusions, rollings, seamless pipes, and forgings for critical defense applications. And all these materials are type certified, and most of the aerospace programs are using this kind of materials for their own activities. I think a lot of work things has already covered in the aeronautical systems, but I'll go on to give only 1 or 2 examples. We did a lot of work in inverted casting technology. We developed for extremely complex and thin-walled aerofoil castings, both in directionally solidified castings as well as single crystals. Certain products of BS and EQAX technologies we have transferred to industries such as HAL Coraport. And in fact, single crystal casting technology for HPT blades and vanes has been successfully developed, and we also developed thermal barrier coatings on these parts are demonstrated. In fact, the potential of this technology is being explored for civilian spin-offs for the manufacture of large-size blades used in land-based turbines for power generation for a BHEL and NTPC. So today, if we look at in fact, the temperature capability of a superalloys is reached saturation. In we have this new generation superalloys and materials such as carbon metal matrix composites, we need to develop it to enhance the engine thermal performance. In addition to that, we are going to work on repair and refurbishment of most of the thin foil aeronautical components. And we're also working on double-walled blades so that we can able to enhance the efficiency of a turbine. As you know well, DML has successfully developed indigenized technologies for production and processing of high-temperature titanium alloys for aerospace applications in collaboration with Vidani and HAL Bangalore. And in the coming years, we're trying to work on advanced composites and to replace certain nickel-based superalloy components in the sections of engine, to reduce the weight. We're trying to work on gamma titanium alloys and so on. This activity is going on right now on a program. And we're also working on several titanium alloys, indigenizing and type certifying for the AMTA programs. As you know well, because we established near-net shear components of various titanium alloys, that is IM685 and Titan 26A for outdoor engine. It is very clear for bulk production, and we're also working to develop the technology for a location-specific microstructure. For example, bliss, we want a equax structure in a disc and a core structure in the blade. That kind of a technology is already established. And in the future, we're trying to see that can we able to produce titanium aluminide for disc applications as a one? Can we use additive manufacturing to produce this? That activity just we initiated. In the field of naval systems, because Indian Navy is interested steels which is having 1,000 MPa and more. In fact, we indigenized ABS steel and AB2 steel, and AB3 we have absorbed the technology, and right now we are working with 1,000 MPa steel because that is required for the high strength levels as well as blast resistant applications. We are looking beyond present also because depending upon the user needs, and we are working on development of smart hull materials. That is a requirement for Indian Navy. We just started an activity on that. When you look at most of the metallic materials, today we are developing through a trial and error method. From the concept to the final scale production, it's taking nearly 20 to 25 years. So can we able to compress these development cycles to a practical limit? So we have to evaluate scientific methodology to replace traditional empirical methods. So for that one, we are trying to work on using integrated computational materials engineering. So when you look at today, we can able to design component, we can able to manufacture it, model it very well. But the question is, we are not able to model the materials because of the large complexity involved in that. But there are several success stories. People use it, ICME, and they cut down the vertical development cycle from 20 years to at about 10 or even less than 7 years or so. So we have taken up an activity of production of powder metallurgy disc using ICME approach, and we are interacting with the various academic institutions in the country, and we are working on this project. Probably we can able to make an alloy, and we can able to model in each activity through integrated computational materials engineering route, and so we can able to complete the integrations from atomic scale to product design and performance in the reasonably 10 to 15 in 5 to 7 years or so. So as you know well, because we are having a lot of expertise in the field of plastic toughness and mechanical behavior of materials, and we have recently completed one project where we could able to enhance the life of most of the aeronautical components, especially engines. And so based on that one, today a major program we have taken up addressing the live revision of fighter aircraft engine, which is closely monitored by the Indian Air Force. And in fact, this particular program, we are going to work on remaining life assessment of a frontline fighter aircraft engine that clearly that is the mainstay of the Air Force for at least 30 years to come. And this activity is going on, maybe in another 1.5 years, we can able to look for the scientific methodology, how to enhance the remaining life of these particular components. In the field of functional materials, because we are mainly working on magnets that to high energy products, basically samarium cobalt, and we could be able to make the different kind of magnets, and we are supplied to the various missile, aerospace, and space program activities. And today, because we are supplying all kind of magnets to to all the three departments. And IRL is setting up a plant at Vizag based on our technology, what we have done with DMRL on submarine cobalts. That activity is going on. And we are also working on NDAB class of materials for various automobile applications and so on. And in the coming years, okay, we are trying to work on, can we able to go for the device level kind of components. And we're also working on radar-free magnets to reduce the cost of the things. And can you use 3D printing to make this kind of magnets? This is the activity right now, the present activities going in DMR. And I can able to conclude my talk. Basically, VR lab is involved both basic sciences and technology level, and we're able to realize the commercial production of components for self-reliance. And as I already said, we are going to work, we are right now working accelerated development of optimized materials and products using ICME and artificial intelligence and machine learning. And I hope we can able to make variety of materials in the reasonably limited time. And with this, I'm closing my talk. I'm very thankful once again to the organizers for giving this opportunity. Thank you very much.
Yeah, thank you so much, Dr. Reddy, for that very insightful walkthrough a whole range of activities being undertaken by you and your establishment. In fact, it's been so heartening to listen to you, giving us an insight into every platform that the armed forces are using today. You are at the forefront of having either almost provided the solutions, or you have a proper roadmap and a vision for providing futuristic solutions. The way you are taking up collaboration, particularly with Minhani and the other industry players, is at the heart of your approach. And I think our session, this session, as well as the coming sessions, and all our listeners and viewers will benefit from the insights that you have provided. We compliment you for all the achievements, and we wish you the very best for success in your future endeavors.
Thank you. Thank you, Steve.
And now it's time for me to introduce the chair for the session. And ma'am, we are sorry for the delay. Okay, Dr. Seema Vinayak, scientist H, director of solid state physical laboratory, has more than 30 years of experience in indigenous development of high frequency semiconductor devices. Very, very important for all of us. And monolithic microwave integrated circuits for strategic applications. Very critical area indeed. An accomplished and acclaimed professional, she has done pioneering work in these domains. In this session, she has got a host of domain experts, including ones from Midhani, from RD, AQA, etc. So we are sure, ma'am, that we're going to be having a very interesting session with you. Over to you.
Thank you, General Srivastava. I've been with the event since morning, and it's been great to see that such a workshop or such a seminar has been organized. In fact, I'm so happy to see two of my colleagues here, Dr. Madhusudan Reddy and earlier Dr. N. Iswara Prasad. In fact, when I got this invitation from Center for Joint Warfare Studies to chair one of the sessions, I did think that since semiconductors is nowhere to be seen in the advanced materials, maybe I'm not the right person to chair a session. However, I'm really thankful to the center for giving me this opportunity, because this gives me a chance to see the requirement and the technology advancements that have been achieved in this area. In fact, when I read that it is a session on the advanced materials for specifically for missiles and artillery guns and naval warships, the thought that occurred to me was that being in the semiconductor area, I know that the advanced materials are all required for, and the technology advancement in this area is being driven by the need for stronger, lighter materials. At the same time, when it comes to semiconductors, it is actually the guidance, the navigation, the control that comes with the semiconductor materials. And as said right in the beginning of the seminar, that chip fabrication is something that India is looking for. And I would say yes, when it comes to silicon chip fabrication, we have not started that at probably the time, as early as the time it should have been taken up. However, we have SCL who's working in that area in Chandigarh. Just like in any advanced materials, maybe it is metals, polymers, ceramics, or semiconductors, the advancement is always as per the requirement of the time, of the warfare strategies. And earlier, although silicon is the most used commercial semiconductor, but when it comes to the requirement of very high power and high frequency communication, or maybe the guidance control, it is these other compound semiconductors that bring the solutions for us. And the semiconductor industry is moving towards higher bandgap materials, wider bandgap materials, for the simple reason that they can provide us much higher powers, they can provide us good tolerance to temperature, and they can also give us much higher power with small size. So with a very good swap ratio, size, weight, and power ratio, it is the higher bandgap the compound semiconductors that the world is moving to, specifically for the defense applications. And therefore, at SSPL, it is the gallium arsenide and the gallium nitride semiconductors that we are working on, and the technologies that have been developed here, we are passing them on to GATEC for production. And whereas GATEC can provide gallium arsenide based MMICs up to the car band, and we proudly have them utilized in many of the ISRO programs like the Cartosat or the remote imaging satellites. And gallium nitride for all ISA radars is required, and we are in the process of delivering these from GATEC, MMICs for these from GATEC. The other thing that is important is if the missiles need, say, IR guidance, or the RF guidance, or maybe the laser guidance, it is again the semiconductors that bring the solution. So lasers that we are working on based on 3-5 compound semiconductors, specifically gallium arsenide based, and the IR detectors based on mercury cadmium telluride, or the type 2 superlattice structures. These are the ones. So I would say, yes, my colleagues in DMSRD or DMRL are working for the solutions of the materials that actually build the ships, that build the missiles. But the smallest components that are not visible to the eye, but are responsible for the functioning of these, for the guidance, for the control of these, is coming from the semiconductors. So I would also request the organizers that we should also have one session on advanced semiconductor materials next time that we think of having a workshop on advanced materials. With this, I would just say that it is the how important the materials are, that we come to know from the very fact that our entire history is classified in terms of the dominant materials that were being used in a particular time, in the particular era. So we have the Stone Age and the Bronze Age and the Iron Age. And if we have to announce, if we have to give some name to the present era, it is the Advanced Materials Age across all classifications of material. And in fact, the last session on smart materials is something I would say that the subset of smart materials out of the advanced materials is something that is the leading edge of development. And the materials that are existing to enhance their properties, we change certain things in them. For example, in semiconductors, we make some heterostructures to use the same materials at much higher frequencies. So this is something which is highly codependent. It is because the technology exists to build such materials, so we are able to advance the materials. And also because we are able to advance the materials, we can have the technology, the solutions that are really the ones that were once a fiction, but today a reality. With this, I would now start. We have a very well-planned session. And in fact, I would request my colleague, Dr. Reddy, to continue to be in this session and more like a co-chair, because he would be able to, to be able to actually appreciate all the speakers who are coming in the session now. The first speaker we have from Midhani, Dr. Rajshekharan, who will be talking on the key challenges in meeting the requirements of advanced materials for defense and aerospace in India.
Thank you, madam. Thank you and good afternoon, all the participants. Let me share my content. Yeah. Once again, good afternoon, everyone. Incidentally, I'm happy that we are following DMRL, the presentation by Dr. Madhusudan Reddy. As you all aware, Midhani has been an offshoot of DMRL, established for the sole purpose of having a self-reliance in the field of material manufacture, particularly for defense applications. This self-reliance concept we are now viewing with a renewed vigor based on our government's Atmanirbhar Abhiyan. A few slides. Sorry. Is my presentation visible, madam?
Yes, yes, it is. It is.
Can you navigate between slides?
Yeah, that's what it is. Still, it says sharing the presentation.
Are you unable to change the slides? Yeah, we can see the second slide.
Yes,
that is
yes.
fine.
Thank you.
We can go to the.
Yeah, I have a few slides before I present you the
slideshow mode also.
I think it's taking time. I'll keep talking, madam. Before I present you the activities of Midhani and our contribution to the defense sector, and then the present recent developments are in the areas of advanced materials. A few slides will be on the initiatives of governments or opportunities we are looking at in the defense sector, particularly the indigenization aspects and all challenges. And subsequently, I take you through the facilities available with Midhani, the materials what we have been manufacturing for defense sector, and the new alloys which we are eyeing at. Yeah, as a commercial organization, we always look at the figures, business figures, where we find interest in. We are still importing a lot of materials with respect to superalloys, special steels and titanium alloys. Significant volumes and valued materials are being imported. This is the global market size of aerospace materials, probably the organizers, and most of you will be more aware of all these things. The initiatives by the government, which are making us to work in this area with renewed vigor. Challenges. These have been the challenges of Midani. Since this unit has been established for self-reliance, the target was to produce several kinds of alloys under one roof. The facilities are set up for making different things, but often not suitable for making for bulk production of any particular item. That makes us a little costly with respect to some of the products, and it continues to be so. Now we are upgrading our capacities, which is making us more competitive. That slides subsequent slides I will tell you the details of those things. In the defense sector, the presence of Midani and the materials manufactured by us, we are into core metallurgy. Mostly they're all metallic materials only. The concentration is special steels, titanium alloys, and superalloys, and more or less the same categories appear in all sectors of defense, as well as space. Space is another area where we get a lot of business or a bulk business for us. Briefly, a profile of Midani is with more than 40 years of expertise. Fields for which we support us. Space is the major thing, and followed by defense, aerospace, and nuclear sectors. Product variants are like this. We have iron-based, cobalt-based, and nickel-based superalloys, special steels of austenitic, martensitic, and precipitation hardened grades. Supplied in the form of basically semis. We often supply even ingots and slugs. Slugs used for applications like gun barrels. Forged products is another area. Forged rolled products, hot rolled as well as cold rolled products, and wires, fold-on wires. Fold-on wires, we also have been supplying welding consumables for some of the naval projects almost for the past 20 years. These are the specific areas in which we are contributing. Land-based systems, we have special steels. Categories are again the same thing, same categories. And if you see look at the products, important products, gun barrel has been an important product, and breech blocks and breech rings for these MBTs. And we have we have got a TOT from DMRL for these armor panels. We are into making up body armor panels as well as vehicle armor for VIP movements and all. And also the main battle tank MBT armoring also we have been doing with the technology available from DMRL. So most of the technologies, whatever developed by DMRL, they come to Midani for productionization, and armor is one area which has been quite successful, and we have made a lot of business in this area. Some other components for this land system. ultra high strength steel for booster motor casing, rocket motor casing, and satellite launch vehicles. Margin steel is, as you all know, that is one of the workhorse alloy. And alloy 172 and 155, they are used for the many of these ordnance applications. We also have an investment casting plant where we produce bodies, pistol bodies, and things like that. These are our armor products, body armor products. Body armor, we have moved on to, from the steel-based body armor, we have moved on to light armor materials. Ceramics, and then followed by even this Kevlar and Dyneema kind of composite materials. And we are able to achieve the same protection level with these technologies as well. All these come under the armor-based products, what you've been doing. This Mi-17 helicopter armor, this is again one more technology given by DMRL, which was productionized and successfully supplied for a battery of helicopters. These are for personal movement armored vehicles and VIP movement cars. Naval systems. Navy is another sector where we have been doing a lot of work. We were supplying the DMR 249 AB class of steels, forgings we have been supplying. Though we do not have, our facilities are not adequate for manufacturing the plates for the hull fabrication or the shipbuilding industry. We have been supplying forgings, and we have been supplying weld consumables for this. And we also supply titanium alloys for the purpose of walls and seawater filters. This is the latest development from Midani side, these castings for the Indian Navy, and fasteners of very special grade materials. This titanium castings, for the first time in the country, we have started making. This is a big 75 kg casting manufactured by Midani. Here again, we have the help of DMRL for hot isostatic pressing. Aeronautical grades. Again, we have several aeronautical grades. Several alloys have been type tested. Ado disc, again a TOT from DMRL, and in fact produced using one of their facilities of isothermal forging. Aluminum alloy castings. Some of the products are we outsource a lot of activities, and wherever our facilities are not adequate, we go out and get things done from outside. Bombshell assembly. This is another it's an outsourced product, but material, basically material and whole thing is coordinated by us only. Yeah, space products. Space, as I said earlier, we supply marine steels and several titanium alloys, and bulk of the business comes from this sector. Many components of this rocket motor casings are made out of Midani-made alloys. Other critical products are products of importance for Midani are these titanium gas bottles. These hemispheres are formed by superplastic forming, followed by EB welding, or even TIG welding can be done. These are for fuel bottles. And again, investment cast products used by the space. And C103 is an
Rajshekhar, I would request you to wind up in the next 2 minutes.
Sure, madam. Castings for cryo engines, all for space program. Yeah, we will come to the latest, some of the latest developments. We have recently made a rolled homogeneous armor steel, which is used for ammunition testing of missiles. This has been indigenized this year. And another one is a very high strength alloy, which is a precipitation hardened alloy, which is almost, which will replace margin steel for some of these missile components. Titanium alloys for aero engines, both for engine materials as well as for structural components. Rings for VSSC. And this is for a oil and gas sector component, again a precipitation hardened steel of a large, very large size. As per the international standards, this material can be used only up to 250 mm rolling section. But here the customer wanted something like 600 mm side sections. The challenge in this case is to maintaining the homogeneity of composition as well as properties of this block. This we have successfully made. And this is the casting earlier referred to. This is a titanium casting, the biggest size we have produced so far for Navy. Ado disc for, engine disc for Ado. Several of the several boards are made for aero engines. We are going to have a wide plate rolling mill, which is capable of rolling up to 3 meter width plates and length up to 15 meters. This will be a big facility which will be useful for armor applications, shipbuilding industry, and even our own margin steel plate rolling and on the what. For which right now we depend on steel plants like Rourkela and Billai. Armor, we are going to have a separate facility, separate division at Rohtak. We are having to have a full-fledged facility will be having for armor alone. And we are getting into additive manufacturing business where, a lot of components of advanced materials are required. Since we have been making materials, alloys, whatever we want to make powders out of that and get into the 3D printing of the same thing for the critical components. Aluminum plant, Midani is coming up with a joint venture with NALCO in Andhra Pradesh. And we are also, our R&D is involved in artificial intelligence and ICM kind of things. These are our development areas. Thank you, madam. Thanks.
Thank you very much, Dr. Rajshekharan. One looks at such presentations and we know how realistic the dream of Atmanirbhar Bharat is. You know?
Yeah.
So thank you very much.
I'll add a word, madam. In fact, I'm not sure. Actually, I presented on behalf of my CMD because he is occupied with other things. Anyway, I tried to do my best in this. Thank you so much.
Thank you very much. Thank you. I'm told that the next speaker from Ordnance Factory is not here. So we go straight away to the third speaker, who's Mr. R. Jai Ganesh. He is the Director, RDA QA, and he'll be talking on specifications and standards, quality assurance and certification. Do we have Mr. Jai Ganesh here?
Yeah, just a moment. Let me. General Arora.
Yes, sir.
So, Mr. Jai Ganesh was to now step up
He's here.
Yes, just put him through and this presentation can
Yeah.
be taken.
Dr. Rajshekhar, could you close this? Could you stop sharing? Yeah. Mr. Jaganesh? Let me call him.
Yeah, we can view your presentation, Mr. Jaganesh. Kindly put it in the slideshow format. Thank you. We are unable to hear anything from your end. Have we lost contact with him?
Yes, he is. He has disappeared from the screen. Madam, can I suggest we move on to Vineet Tiwari, Commodore Vineet Tiwari.
Okay. Are we sure we are disconnected and therefore we can take the next one?
We can take him back when he comes.
Yeah,
Okay.
we'll get back to him later.
Okay. So while we wait for Mr. Jaganesh to get reconnected back with the event, I now request Commodore Vineet Tiwari from Naval Design to present on advanced materials for naval shipbuilding. He has 10 minutes to present. Yes.
Hello.
Yeah. Yes, Commodore Tiwari, can you please speak up a little so that we know whether we are connected? We have your presentation on screen. That has to go in the presentation format. However, your voice we are yet to know whether we can hear you.
Vineet, go to the PowerPoint. Yeah, there you are. Yes. Make it full screen, please.
Okay. Here in the slideshow mode, yes, we can have it like that. Yes.
But we are yet to see and hear you.
Yeah, yeah.
Are you able to hear me now?
Yes, yes, very clearly.
Right, ma'am. I have permission of the session chairperson to commence my presentation.
Yeah, yeah. Please go ahead. Please go ahead.
Yes,
The
please do.
session chairperson, Dr. Seema Vinayak,
Yes.
distinguished speakers of this
Yes.
session and participants, very good afternoon to all. May I continue, sir?
Please do. Please do. Please continue.
At the outset, I would like to thank the Center for Joint Warfare Studies for taking the initiative and providing a forum for information exchange and knowledge sharing on a very relevant topic of advanced materials for defense and aerospace. Over the next 10 minutes or so, I will present my views on this topic with architect in the company of eminent professionals in the field of material science in this session of the webinar today. I am no materials man, but I hope I'll be able to give a good user in my talk today. Ma'am, the scope of my presentation is flashed on the screen and will cover the genesis of indigenous warship building, warship construction materials, advent of materials naval shipbuilding, and key takeaways from Navy's perspective with respect to composite materials. I'll begin with a brief background of Indian Navy's design organization and the warships designed and built indigenously. The genesis of the Navy's design organization lies in setting up of a small central design office by the naval visionaries in 1964 to set the nation on course to become Atmanirbhar in design and construction of naval warships. The design organization has progressively grown over the past 6 decades to its present form, where it is steering indigenous design and construction of most potent corvettes, frigates, destroyers, and aircraft carrier. A glimpse of some of these ships will be shown in the next few slides. This slide shows some of the landing craft utilities, survey vessels, and LSTs designed by the design organization. This slide shows a few corvettes and frigates designed by the Directorate of Naval Design. And this slide shows two classes of destroyers which have been built and delivered, and three major ongoing projects of the indigenous aircraft carrier, a P-15 Bravo destroyer and a P-17 Alpha frigate. The next few slides will highlight functional requirement of shipbuilding material, how these materials have evolved, and the utilization of composite materials in warship construction globally. The major factors which govern the choice of material for warship construction are shown in this slide. A warship structural material should be such that the platform remains capable of performing its designated mission under hostile marine environment and close contact weapon explosion loads over the entire service life of 25 to 30 years. Prior to the 19th century, ships were built using wood. The metallurgical evolution brought in mild steel ships with bolted and riveted connections, followed by all welded steel huts. With several cases of brittle failure in mild steel ships like the Liberty class in 1940s, high strength steel with better notch toughness were developed, which became the preferred choice for ship structures, particularly for the warships. The aluminium, with its advantage of lightweight, has been widely used in hull or superstructure wherever weight was a critical aspect in design of a ship. Since last quarter of 20th century, GRP and advanced composites became the preferred material for specific applications due to its advantages of low weight, radar transparency, and non-magnetic property. Composites as warship construction materials has a distinct advantage of being non-magnetic and therefore finds specific use in construction of hulls of mine-laying and mine-countering vessels. Beyond this role, composite materials have been used for construction of smaller warships such as Visby-class corvettes of Sweden and few other smaller vessels of other foreign navies. The entire superstructure of recent Zumwalt-class destroyers of US Navy has been made from composite material. I'll just show a glimpse of these crafts in the next few slides. This slide shows some of the well-known mine countermeasure vessels made of composite material worldwide. This slide shows Visby class corvette, where the entire hull of the ship has been built of composite material. This is one of the largest corvettes which has been built. Zumwalt class destroyers, as shown in this slide, have the entire superstructure which is built of composite material. A peculiar aspect of the superstructure here is that there are no yardarms for mounting of radars and sensors. Instead, planar arrays have been used on the walls of the composite superstructure. In contrast to Zumwalt, the Indian Navy destroyers have large numbers of rotating sensors requiring large physical separation, due to which the masts made of steel have a large number of yardarms as shown on this slide. It is envisaged that with the availability of planar arrays in future, either through indigenous development or procurement, we will be able to introduce integrated masts made of composite material, which will be a major improvement for our future platforms. Over the next couple of slides, I'll briefly run down on the advantages and disadvantages of composite material in context of warship construction. The advantages of composite materials are well known as shown on this slide: lightweight, corrosion resistant, radar transparency, and non-magnetic in nature, which makes composites very suitable for specific applications in terms of naval warships. However, a major disadvantage of composite from warships perspective is its susceptibility to fire. Accordingly, additional fire insulation, fire detection systems, and firefighting systems have to be provided inside composite structure of warships, which add to the cost and complexity. From strength and stiffness perspective, composites have to be accorded much higher thicknesses as compared to steel, which results in reducing the internal volume on warships, where space is as such at a premium.
दो जय गणेश तल्लूर दो
In
रहते
the
हैं
next few slides,
मतलब कि
I
आधा
will
घंटा
provide an overview of indigenous shipbuilding material.
Are you hearing me, sir?
General Arora, I request you to kindly mute your mic. Yes, please continue.
Yes.
Commander Tiwari, yes.
Thank you, ma'am.
Yes.
The material choice for a platform, marine platform, depends on its size, role, and other design considerations. High-strength steel is a preferred for construction of major warships because of its superior mechanical properties and ease of fabrication for ships. Aluminium is often used for applications where low weight is a key design driver, such as high-speed, fast-attack crafts or superstructure of missile boats. Both high-strength steel and aluminium have been indigenized by DMRL for warship construction and have since been standardized for rationalization of steel inventory, weld consumables, weld procedures, and welder qualification. The Indian Navy has pursued extensive use of composite materials wherever low weight and high speed is of paramount importance from design consideration. All boats and high-speed vessels such as immediate support vessels and fast patrol vessels are built from GRP and composite material. The superstructure of the last two ships of P-28 ASW corvettes have been built from CFRP material to reduce the top weight and improve the stability of the platform. All the bow-mounted sonar domes are now being constructed from GRP or CFRP, due advantage of being lightweight and superior acoustic transparency. I'll just show a glimpse of these applications in the next few slides. Some of the GRP boats of Indian Navy are shown on the slide. The composite superstructure of P-28 ASW corvettes is shown on the slide. So this entire superstructure is made of a composite material, which is a very unique and first time attempt by the Indian Navy to integrate on a steel hull of this size. And this just shows the hangar opening of the composite superstructure. The sonar domes of two recent projects are shown in this slide. The P-28 dome is imported from UK and it is made of carbon fiber reinforced plastic, whereas P-15 Alpha dome is indigenous and made of GRP. This has been developed by R&D and produced by Keneco Goa. Due to superior radar transparency, composites are extensively used in radomes on the superstructure of the ships as a cover for various radars and sensors. Also, upper deck fittings such as ladders and stanchions made of radar transparent composite material have been developed towards reducing the RCs of the ships. Looking at the challenges in our ecosystem with respect to use of composites for large structural applications, there is no single nodal agency in India which has the overall capability of load computation, structural design, and design validation with respect to composite materials for large warship constructions. Navy had to rely on Messrs. Saab of Sweden and a foreign classification society ENV for design and construction and certification of composite superstructure for P-28 ships. To conclude, in the present times, high-strength steel is globally preferred for construction of larger warships. Composites are extensively used for smaller size vessels and crafts with high speed requirements. The same is applicable in context of Indian Navy also. Coming to the way ahead, Navy is very keen to utilize advanced composites in the superstructure of future combatants. Towards this, we are closely monitoring the performance of the composite superstructure installed on our ASW corvettes. Based on a comprehensive assessment of all important aspects, we will chart a firm way forward for introducing composite superstructures and mass in our future major combatants. Also, Navy is looking forward to introduction of unmanned aerial, surface and subsurface solutions in a big way, for which advanced composites will be the primary material. With that, I have finished. I would like to thank the organizers for giving me this opportunity to deliver my talk. Jai Hind, Shano Varuna.
Thank you very much, Dr. Vineet Tiwari. It was a very, very interesting talk. And you, in fact, gave the complete picture in the good time of 10 minutes alone. So thank you very much. I have a few questions and I will wait for the Q&A session to ask this. I think others would also be having some. I am sure that you'll continue to stay with the event till we go to the Q&A. Now I request Mr. Dinesh Talur, the Head Portfolio Development, Siemens Industry, Software India. We'll be talking on Siemens multi-mechanics. If before Mr. Dinesh Talur, we can take Mr. R. Jayaganesh, if he has been able to reconnect.
We can see.
Are you hearing me, madam? Are you hearing me?
Yes. Okay, you could reconnect back. Okay. So before we go to the industry speaker from Siemens, I request Mr. R. Jayaganesh, Director RDA QA, GWM, to give his talk on specifications and standards, quality assurance and certification.
Good afternoon, madam. Are you hearing me, madam?
Yes, very clearly.
Yeah. So I will be covering the specification standards, quality assurance in general, because RDK, DWM and M is dealing with the aircraft materials only. But since the topic is given in general, I will be covering the general quality assurance topic. Next is certification, and finally the conclusion. My presentation structure is of specification and standards, quality assurance, certification, and finally the conclusion. Metallic materials form the backbone for the aircraft, aero engines, missiles, naval warships, artillery guns. Typically, materials are selected for a particular application based on the component design and environmental conditions. The development of materials is categorized in two major types. One is the AB initio development, wherein the international standards are not available. Next is the customization of the existing international standards or national specification to suit the end applications. International standards, as we are aware, we are having British standards, AMS, ASTM, Post, AISA standards, DIM standards, French standards, US military standards, and IS standards. Specification of standard for each material is established and standardized to ensure the integrity and consistency of each item it is produced and qualified. In the present scenario, for a single material, multiple equivalent specification and standards are available internationally. Design, environmental conditions, and cost play the vital role in the selection of the material specification and standard. For example, marine steel 250 is a ultra high strength combined with good fracture toughness properties, which make it widely used choice for missile application. However, the corrosive nature of the marine 250 steel is a disadvantage. This marine steel 250 grade is used in leading edge of the LCA aircraft also. As an alternate, the new age missile programs like BrahMos, Rudram 3 are using 11-10 pH steel, which is corrosion resistant. However, the strength level of 11-10 pH is lower when compared to the marine steel 250, which is being compensated and addressed during the design applications. Though the material specification and standards pertaining to a particular alloy equivalent, there are minor differences among them which has to be judiciously studied based on the criticality and end use applications. Marine steel, for example, marine 250, the UTS values as per the ASTM and AMS standards, there is a slight difference. So like that, the other properties also, there will be little differences there. Even the grain size also, in the ASTM standards, it is not mentioned, whereas in the AMS standards, it is mentioned. Specifications and standards for materials are published based on exhaustive data generated pertaining to the processing and the property evaluation. For example, AMS are developed based on the MMPDS handbook, which is an accepted source for materials recognized by FAA, DOD, and NASA within the limitations of the certifications requirement. Missiles, artillery guns, and naval warships, which are manufactured based on the licensing agreement, require the use of materials specified therein by the original equipment manufacturer. Indigenous substitution of the materials, apart from what is specified by the OEM, may attract the certification before it is put into use. The following are the specification standards pertaining to the materials mostly used in the missiles, artillery guns, and naval warships. As we discussed, marine 250 steel is used in the missiles as well as in the LC aircraft applications. 11-10 pH steels, missiles and naval warships, austenitic steels, missiles and naval again warships, titanium alloy again missile and naval warships, and 12X18 Dutch 10-ton steels is naval warships, STA-59 steel, BS-143 artillery guns, and the Russian specifications in naval warships. Midani has also developed Indian 250 steels, it is already discussed, and austenitic steels also they are developed, low alloy steels also they are developed. Again, the titanium alloys also they are developed for naval warships. DMR will also develop a common strength shipbuilding steel class of steels, that is ABA DMR 249A, AB2 DMR 249B, using the infrastructure existing within the country. The materials are currently being produced by the PSUs private firms like SR Steels, say, under the transfer of technology. Private firms like various aluminum and steel alloys are developed by many private firms for use in missile programs. Firms like Bharat Forge, Pune, PTC Industries, Lucknow, Sunflock Steels, Nagpur, Manjira Machine Builders, DSPL, Rachamalu Forging in Hyderabad have demonstrated the capabilities in the development of various forgings and castings made of steels, titaniums, and aluminum alloys. Quality assurance. This made is a general quality assurance. It is not specifically pertaining to aerograde materials. Since the topic is given as a general for both DGAPA, DGPA, DGNI, I made a general procedures. Quality assurance is encompassing inspection, testing, evaluation, and certification of materials, provides the guarantee for reliable performance during its operational usage. QA authorities shoulder the prime responsibility for the safety and reliability of the material. In the development phase, the primary role of QA is to detect the design deficiencies during qualification testing as a part of the certification. In view of the critical safety aspects related to the materials used in the aircraft, aero engines, missiles, bombs, artillery guns, and naval warships, inspection clearance by an independent quality regulatory agency is mandatory. As such, is followed by many countries. The regulatory agencies coordinates and ensures the establishment of a robust quality system, not only by assessing the product testing, but also through controlling the various process parameters, anticipating the potential failures during the service use, and simulating the operational requirements as applicable. Importance of QA for materials. The requirement of material is to execute the requisite mission without any hazard during its operational performance. Failure is not an option in any system, since the consequences may be grave and leads to catastrophic failures. The quality requirements are therefore stringent. The quality assurance plans are accordingly put in place to ensure that a defective store is not certified. When any store involves the material problems, the QA scope broadens because of the wide range of processing variables associated with each material. Although different agencies are involved in achieving the desired product quality, the QA group has a prime responsibility for achieving the high reliability product and the personal safety. Generally, for aero-grade materials, the quality management system to adhere to the AS 9100/2016. For others, ISO 9001 and 215. The laboratory test procedures should be accredited in conformance with enabling requirements. For all special processes like heat treatment, plating, NDT, the manufacturer ought to establish conformance with NAPCAP approval is preferable. In certain of the cases with DGAQ approval and DGK approval, DGNA approval, they are proceeding with that is also allowed. These guiding requirements provides the confidence that the manufacturer quality system will produce a material that will meet these specifications. The principal guiding documents for missiles, artillery guns, and naval warships are ADP mass for aero-grade materials, that is for air-launched missiles and air-launched bombs. AFQMS, that is approval of firms and quality management system for DGAPA, DDPIL for DGPA, and ASS for DGPA, and quality management and improvement plan for MSPA, and MQP plan for the MSPA. Modes of inspection. Basically, there are two modes of inspection during the development and subsequent production phases for stores. The first is direct inspection, in which the QA is involved in QA activities. The second is called the surveillance mode, where all inspection and testing activities are carried out by the QC personnel of the manufacturing agency under the supervision and control of QA authority. However, all the critical stages of inspection, test, and re-verification are checked by the QA authority as per the respective approved quality assurance plan. As DGA we are having different plans of executing the quality assurance. We are having three modes of inspection also, sometimes where we are having the subcontracted firms. Subcontracted firm QA will do the first QC work. Then next is the main firm will carry out the QC work. And finally, where the critical stages are concerned, DGA will carry out the quality assurance checks. There are three types of this thing during the development phase, one, and during the production phase, and during the service exploitation phase. Strict quality assurance results in defect-free exploitation of stores throughout their assigned life, though the material cost is bare minimum against the total cost of the missile, artillery gun, or naval warship. Keeping in view the end use of the item exploitation during emergency, compromise on quality requirements are not permissible. Material production is a process-oriented activity requiring complete control during melting, processing, thermomechanical working, and heat treatment from the input stage to the final product. This means close monitoring of critical process parameters within process, inspection, and testing for each batch of material. Since different materials have different characteristics, each will require a specific quality plan for ensuring the final product quality. Certification. Certification of material is a requirement for use of the same in missiles, artillery guns, naval warships. Certification involves the design and development agency, manufacturing agency, QA authority, and the certification authority. The entire activity of certification is to establish the process and ensure the suitability of the material for end-use application. Typical certification process of something we are given below. The main contractor, that is the design development agency, needs to approach the certification agency with the project proposal and design criteria based on the user requirements. The certification authority studies the design criteria submitted by the design and development agency and finalize the technical certification requirements in consultation with all stakeholders, that is design and development agency, manufacturing agency, QE authority, and certification authority. Based on the certification requirement issued by the certification authority, the manufacturing agency shall take up the processing and property evaluation activity in coordination with QE authority and again with certification authority. Further, the main contractor forwards the QA certificate results pertaining to the processing and the property evaluation to the certification authority, who shall review the same with respect to the certification requirements and accords clearance to the material component. Certification of materials may be as applicable requires the main contractor to demonstrate the repeatability of the process and properties in consecutive batches, which forms a basis for the certification agency to accord approval for bulk production. The certification activity is aimed at ensuring the integrity within the batch and consistency among the batches. The following are the certification and QA authorities for development of materials for missiles and artillery guns and naval warships. For missiles is concerned, CEMILAC is a certification authority and DGAQA is the QA authority. And for artillery guns is concerned, Directorate of Qualifications Armaments, and again QA authority is Directorate of Qualification Armaments. They go by DSS, DDPA, and the developing agency is DRDO, Bell, OFB, and private firms. For naval warships, Center for Certification of Naval Materials are there. QA authority is again DMDE, Defence Machinery Design Establishment. It is under the TOT. And Midani is also developing the NMRL, DMRL, SAIL, the SR Steel, LNT, and other groups are also developing the materials for the naval warships. Finally, the opportunities are endless for materials in missiles, bombs, artillery guns, and naval warships, including aircraft, aero engines, UAVs, etc. Any relevant manufacturing production agency or private public sector can explore the possibilities of becoming a potential vendor of materials under Atmanirbhar Bharat and Make in India initiatives of the Government of India. Over a period of time, material development agencies like Defence Metallurgical Research Laboratory, Midani, under the umbrella of Ministry of Defence, and several private firms have established the technology for producing various metallic materials such as maritime steel, austenitic steels, PH steels, titanium alloys, super alloys, aluminum alloys, which are having wide applications in the missile system, artillery guns, and naval warships. Thank you, madam. Thank you. Thank you very much for giving this opportunity. I thank Lieutenant General Sunil Srivastava and Major General Ravi Arora for giving this opportunity. Thank you.
Thank you, Commodore. Thank you, Jaganesh. Dr. Vinayak had to leave for another meeting because we were running late. So we'll move on to the next speaker, Mr. Dinesh Talur. Thank you so much.
Yeah. Hi, good afternoon, gentlemen. Good afternoon, Mr. Madhusudan Reddy, sir. Good afternoon, Major General Ravi Arora, sir, and the chairperson. Thanks for giving us this opportunity to present to you the Siemens technologies, particularly in the world of material science, which is addressing the need for having a virtual material characterization technologies. On behalf of Siemens, again, I once again thank Major General Ravi Arora to give us for having given us this opportunity to present. I will share the screen and take you through the slides that. Just prompt me once you see this. General, could you see this? Can I proceed?
Yes, I can hear you. We can see it very well.
Yeah, thanks, General. Yeah, materials are everywhere, and today we know that materials are being introduced into the various industries and applications at almost unprecedented rate. There is the study which says that 70% of the new products that are getting built or developed in the industry today, which includes the aerospace and defense, they require the new materials. And now these new materials can have to be obviously innovated, and then these can come in multiple forms, where these can come because of the new, some new formulation of the new chemicals, or a combination of some existing materials, or enhancement of an existing available material, or sometimes it could be the new manufacturing method. So all this can contribute to the evolution of the new materials. And it is expected that the industry, the spend for in the development and absorption of the new materials in the industries is actually hitting about $3 trillion. That's staggering, as the chairperson a little while ago said, that this is the age of materials, and then probably we see that this number actually justifies being called the age of the new materials and the advancement of the new materials. And this also gives us the engineers the option to develop the newer materials. Of course, there are myriad of opportunities are there because the degrees of freedom are very high. But since the number of possibilities are also very high, it offers another challenge where they will have to really validate these new materials and then accept them, and validate and actually absorb them for their design and development and developing the new products. And today it depends heavily on the physical testing, because any new material will have to go through this grind of having physically been tested on its specimen before it gets consumed in the material application of the material for the products. In this direction, given the focus and then the mandate for absorption of technologies in it, and give them the substitute for this validation of the materials that are getting built, and then validation and absorption of that into the industry, Siemens has added this new capability of virtually simulating the behavior of these materials, and acquired a lot of technologies and developed in-house also. And with the existing multi-physics simulation capabilities, also infused a lot of development and breadth, which includes the materials as well. So this is a typical scenario in which the materials which are newly developed or upfront validated using the simulation tools before they are consumed in the real world product manufacturing. As the slide says, one way to look at is that the figures here about the time and the cost that it takes to develop a material for the aerospace and defense looks to be a little on the lower side with compared to what Dr. Madhusudan Reddy said a little while in the session, that it is much higher than what it is actually shown here. It is not just 5 years and $50 million. It is much more. He was indicating that the development of new material, actually the time spans go more than about 15 to 20 years and even higher than that. So one way to, and then typically the workflow of how the new material getting consumed in the new product is typically like this, where there is an extensive test campaign where the specimens of the new materials are created, and then there is an extensive physical test campaign is done, and then they are populated into the material database, and then the products are designed and validated, the suitability of these materials to fulfill the functional requirements of that particular product. So this is the conventional way it has been happening. Now, with the increase in demand, what does the industry need? So our understanding is that yes, of course these metrics have to be challenged, and then we will have to reduce the time that it takes to develop a new material and use it for the product development. has to be reduced. So what does the industry need? It needs so that any technologies that can actually help them to accurately and then very fast virtualize the whole environment of validating these materials, and so that they can use it for their the actual end products, whether it could be an aircraft or a missile or a radar or a ship, which we have talked about. So what does the industry currently have? The industry today claims to have a lot of technologies which can digitally twin the materials. There are a good number of technologies available to understand the behavior of metals each in isolation. There are good tools which can help you in doing this in a product design using the various materials. And there are separately a different set of tools available for studying how the new materials can be evolved and then they are studied. And also there are a lot of technologies are available where you can test the behavior of the metals based on how they are produced. So all these are available in isolation, but then what is missing is the integrated environment which connects the materials which are involved and then which are being studied now currently in different isolated way. And so what is common in all these different tools and technologies which are currently being used is what the common link among them is the microstructure, and then we have very limited tools in the industry today which can help you to truly model this microstructure and then take it up to right up to the macro level. So this is the reason why we thought that a tool like this would significantly add to the industry and help them to create an environment where the multi-scaling, right from microstructure to the behavior of the material when it actually becomes a part and or a component or a system, and then how it behaves in its macro environment. So the one intent was to see that yes, this is a very gaping gap in the industry's usage, and then so that is how Siemens believed that we can help the industry with this. And then as it says, and what does it do actually? The multi-mechanics. It basically helps you to understand the behavior of the metals from both the micro and then the macro scale. While the failure or the damage can happen because of a variety of reasons, and then there can be a myriad of possibilities to do that. What is required is a very accurate simulation tool to model the behavior across the multiple scales. And when it is easier to say that, but what exactly complexities are being faced when we actually try to do a multi-scale modeling. So typically at a micro level, when you actually start modeling the microstructures at a micro scale, typically the complexities will involve which will have the voids that could be created during the manufacturing, or there could be cracks which may be initiated and propagated within in the fiber or in the matrix or in the interfaces, or the behavior of the fibers which could be anisotropic and it could be highly nonlinear, and sometimes it could be time and temperature dependent as well. So what we propose to use is that while each individual constituent has a unique behavior, and then the geometry of the whole part that you eventually manufacture also has an important role. So that is how actually about several decades ago the evolution of the finite element method has evolved to ensure that the behavior of the part in the real world is understood in the virtual environment. So we have extended the same technology to do the modeling the microstructure as well. And how we do that is our approach uses the finite elements to model the microstructure and also for a variety of materials. Our tools will provide the capability to automatically generate microstructures for a variety of architectures, including all that is being listed here. I don't want to read that. We have, beyond what has been shown here, right from the porous materials to the chopped fibers and particulates and continuous fibers. We have additional architectures are also being continuously developed, and then they are going through the process of patenting and validation. So what are the other challenges that we face? Is while we have capability to model the various and complex microstructures and its behavior, the bigger challenge comes in how do we actually link this to the macro scale at the product length scale. So typically, as a composite part FUC, like an aeroplane wing, it would be really challenging if we just adopt a typical FEM method, finite element analysis method, to mesh a model which has which can also be modeled as a wing and also at the single fiber. What we do here in this technology is use some homogenization techniques, and then we do the decoupling at the different length scales. Use something called representative models of the microstructure, but will still, which can strongly couple the material constitutive behavior. Why we do this homogenization? The objective of doing this is to obtain the overall material behavior for a representative volume, which is the smallest that we can pick up in the overall architecture, and which requires the behavior has to be consistent at multiple scales. So this RVE, the representative volume element, becomes the key. Is the minimum material volume where the behavior can stay consistent at the different levels, and then the capturing of this RVE is actually called the homogenization, and then that is very effectively can be done in this. So another challenge which comes in the material innovation is the need to do the extensive physical testing, and given the need for very fast technologies required to replace this physical testing, but at the same time, physical testing also cannot be totally replaced. The need for having a multi-scale computational methodology is actually proving to be very cost-effective, and also is becoming reliable and efficient. So in a true multi-scale model, when it is created, we attach that unique independent microstructure model to the finite element model, and there is a continuous communication between the scales that brings the accuracy of the predictions of how these material behaves in different scales and consistently across the scales. So apart from the ability to do that multi-scale modeling, this technology also offers certain capabilities to do the implicit and explicit solvers as well. As you see, the behavior, the disorientation of the various fibers, and then the matrix, depending on the impact and how it can be captured in the real time, there is just a quick animated illustration of how the tool provides the capability to predict the behavior at different physical loading scenarios. So there are, of course, it is not that we are trying to do something very unique and very out of the world. There has been a practice to do this. It is called FE2, which is essentially the micro scale modeling, but then the the tools that are available are computationally, very time consuming. And so it is actually not possible for the industrial applications, the current one. So that is where we actually stood out and then did a few benchmarking examples where the time that is required to actually characterize these materials has come down to almost, you can see, 99.9% reduction in terms of the runtime required to do this multi-scale modeling. Instead of the time that is shown in the red is where the microstructure is modeled using the typically FE2 techniques, and the time that is consumed by using the multi-mac. Relating to the slides, a couple of slides back which I showed, where the material where this is the place where there was an extensive creation of the material library using the physical testing, and then using it for the physical behavior and also the understanding and the response of the product to the physical loading conditions is now replaced by the virtual testing and also the true multi-scale tool, which is multi-mechanics, which will help you to substantially reduce the amount of physical testing that is involved in creating these material libraries and then using it to apply it for development of new products and the systems that are required and the structures. So this is a quick workflow which is typically involved in the characterization of any new materials, and we from Siemens also can work with you and understand the specific materials that you work with, and then we can develop these virtual material characterization workflows for you depending on what kind of end objectives this particular material is going to be used for, and depending on the configuration and architecture of your the materials that you build. We also work with quite a few academic institutes in order to ensure that there is a sufficient validation, and then the intellectual backing is continuously available to the algorithms and the solvers that we have continuously been developing. And this multi-scale modeling can work with all the industry standard FEA tools and complement it for ensuring that the right materials are picked up for the simulation.
Mr. Talur, we'll request you to wind up.
Yes, Mr. Srivastava, thanks for your time. I wish I had the time to run you through this video, which is it's actually a demonstration of the tool.
Okay, go ahead.
Yeah. Probably I will just. I'll try to make it as brief as possible and see that the narration is understood by the audience. It is an existing part which has been picked up to see the microstructure behavior of it. And as you can see, we have picked up an existing material model in this, and we edit it to create the different homogenized properties. We pick up the microstructure model, which is already available across, which is the one which has been picked up is with the voids here. So once this is done, as you see here, and this is the typically from here, it is more or less the workflow is same, where you have typically you start with the material and the properties being defined in the library. Here we are actually working and then manipulating at the library level itself, and then see that the materials are added there. So we select a few locations which are actually called the the preset zones or the pre-test areas within the larger product where we wanted to see this the behavior at the multiple scales, and where we wanted to study the deformation, the stress, and then the crack propagations happening in this whole part, and then all those specified hotspots or the points of interest. However, you can actually build it to extend this specific spots to the entire field in which the whole part also it can be extended there. So the workflow after that is typical of any post-processing that can come out of any simulation workflow. And there you get to see the response to the physical loading conditions, and then the various strains and other physical behavior is captured in this post-processed file that you are seeing. And this is the typical plots where you know that for the given microstructure and then the fund which we have selected, how the behavior or the response of the particular wheel changes with respect to the microstructure that you have chosen. So this summarizes quickly the capabilities of the multi-mechanics technology that we wanted to present to you today. We are open to take any questions which are connected with this. And with that, I wanted to actually show a couple of customers like Airbus and Slovey. We have been using this technology to develop new materials, but then probably I can share with those who could be of interest subsequently. You can connect them online. And
can you conclude now?
yes, sir. Yeah, that concludes my presentation for this session today. My details are flashed here for those of you who could be who are interested in continuing and understanding more of this multi-mechanics technologies that Siemens offers. We'll be pleased to work with you and help you with the more inputs. Thanks, gentlemen. Thanks for your time.
Stop sharing, Mr. Dinesh.
Yeah, I did, sir. Thanks, Mr. Srivastava, sir.
So shall I summarize the session, okay? Because there's no time to take the questions, okay? Then
yeah, actually, there are 2-3 questions since
we can
actually
we can answer online, okay? No problem, because let us summarize it. Okay.
Only Dr. Seema had to leave, so there's a question that I saw, at least 2 of them. One says that because of COVID times, is it feasible to carry out remote testing? This is one question. The gist of the question is that is it feasible to carry out remote testing? The second thing is that they say that while the Navy provides authorized supplier names in specifications issued, the same is not being done for land defense steel requirements. If these questions could be answered.
Sir, first question, can you hear me, sir?
Yeah.
First question I can answer. For non-critical items, we are providing through VC only. All the clearances, everything is provided through VC. All the testing is physically seen from the VC itself, and we are clearing the non-critical items. Whereas the items of critical nature, there also we are seeing through VC, but setting up the critical stages, hold points, we will see directly. That's all about it. Because generally for aircraft applications, there are 3 types of components in the structure wise. One is class 1, class 2, and class 3. Class 1 is highly stressed, and class 2 is stressed but not highly stressed, and class 3 is not at all stressed. So we will go by the classification of the item Accordingly, we will provide the QA coverage.
All right, thank you. So I think now, since Dr. Vinayak had to leave, I'll request Dr. Madhusudan Reddy, if we can just summarize and conclude the session.
Okay, thank you, because I'm summarizing on behalf of the chairman, Dr. Seema Vinayak. Okay, this is a very interesting session. Okay, in fact, we covered many aspects of metallic materials and quality assurance thing and design aspects, whether in naval ships and submarines and when you look at because the last thing which Dinesh Talwar has indicated a lot about integrated computation materials engineering. The most challenging is the multi-scale modeling is maybe easy, but again integration is very difficult. Okay, and because when you look at ICME is a multidisciplinary and extremely broad in its scope, so it is essential to have a multi collaborations to realize the product. And think the country just started an activity, and it's a good to know that a lot of activities going on. Siemens, okay, I think we should be able to collaborate and we should be able to make the material in the reasonable time, because the user is asking the material today, that is asking about the properties, and tomorrow they want the material. That is the day. Okay, we have to really I have to work on this particular area in a larger sense. And in fact, we are collaborating with almost all the institutions in the country, and we are given almost many projects for a given product. We have bifurcated a number of multi-scale modeling things, and we are introducing and we are involving various academic institutions in this thing. And it's very interesting because today we are good at the component design, we are good at manufacturing, we are able to model it. Only material is a question mark. I think that is going to come in another couple of years. So we'll be very sufficient in designing the materials. And Rajashekar has covered a lot on all the materials, especially for titanium alloys, super alloys, and precious ornamental stainless steels. And he has covered not only the materials and the facilities, but what are the challenges involved in that. Nicely covered by Dr. Rajashekar of Midhani. And Jay Ganesh has mentioned many things about the quality. Quality is most important. So he has covered various quality aspects in general and specific to the particular products, both critical and non-critical, and also certification he has covered a lot. And Vineet Tiwari has covered about the steels, which is, he said, that is widely used for the warship as well as submarine applications. And he has also covered some design aspects in detail. So in all together, okay, because this session is very interesting and it's covered many challenging aspects, both right from the experimental to the modeling aspects. So I'm very thankful to all the speakers who could able to address it in the limited time. With a lot of data they're able to present it, and it's very interesting. And I'm very happy to summarize this thing. And thank you very much for giving this opportunity. And we will work together in the coming years. Thank you. Thank you. Over to the
audience. It remains for me to thank Dr. Madhusudan Reddy in particular, that he not only agreed to engage with us on a short notice, but he's also stayed for the entire session. He has also summarized it for us. So thank you so much, Dr. Reddy. On behalf of IMR and CENJOWS, I thank you. We also convey our grateful thanks to Dr. Vinayak. And we have taken a suggestion that in our future engagements, we will weave in something on semiconductors as to how they are critical in every application. I also thank all the other distinguished speakers for their very valuable contributions, also from the industry assignments. So what simulation can do and how it can make processes and save time as well as cost is the way forward. So that came out very clearly. So thank you so much, and I'll request General Arora if you can tell everybody about the next session.
Yes, sir. We will close this session and open the session which was to start at 2:30, but we'll wait 10 minutes for the delegates to gather there before we start. Thank you.
Thank you, sir.
Thank you very much.